In our last video, we were looking at quadratic functions in this standard forms. Remember, ax squared plus bx plus c equals our y, or our f of x. So in these functions, we can now graph them using a table. Now, tables are always helpful with graphing because all we have to do is use our input x, plug it into the equation, and get our output y. And so those x and y's, our inputs and our outputs, become the ordered pairs. So if we plug in 0, 0 squared is 0, 4 times 0 is 0, 0 plus 0 plus 5 makes 5. Same thing if we use 1, 1 squared is 1, 4 times 1 is 4, 1 plus 4 plus 5 makes 10. 2 squared is 4, 4 times 2 is 8, 4 plus 8 is 12, plus 5 is 17. 3 squared is 9, 4 times 3 is 12, 9 and 12 is 21, plus 5 is 26. Now, at this point, we can already kind of see, well, it's getting way too big to fit on our graph. There's no way we're going to be able to fit all of this. Plus, it looks like this is just continue going up, and we know that the parabolas will go like this, but there's supposed to be a turnaround point where they go the other way. And we can't see this turnaround point. We only see it just getting bigger and bigger and bigger. So what are we going to be able to do here to make sure, get rid of some of these, that we can find that turnaround point and make sure that our table is actually helpful? So I'm going to see if I can grab that, get rid of it. And I'm going to let you know the first thing you need to do is find your vertex. Once you find your vertex, you can center your table around that vertex. You saw before as we were trying out random numbers, that didn't necessarily help us. But if you find your vertex first and center it, then we can use that as part of our table. So remember to find your vertex, negative b over 2a. Negative 4 over 2 times 1 is 2. Negative 4 over 2 is negative 2. This is the center. This is my vertex. So here are those numbers we were looking at. The 0 goes with 5, 1 goes with 10, 2 goes with 17, 3 goes with 26. Notice we were pretty far away. We were a couple spaces away from our vertex. So if we continued going bigger, we would never find that turnaround point. So we need to find the vertex first, then we can plug everything in. So if we use that and now say negative 1. Negative 1 squared is 1. 4 times negative 1 is negative 4. 1 plus negative 4 is negative 3. Plus 5 makes 2. Negative 2 squared is 4. 4 times negative 2 is negative 8. 4 plus negative 8 is negative 4. Plus 5 is 1. Now, if this is our vertex, remember there's symmetry around the vertex. So let's just check one more time here. Negative 3 squared is 9. 4 times negative 3 is negative 12. 9 plus negative 12 is negative 3. Negative 3 plus 5 should be 2. So already we can see around this vertex, this is where it mirrored, right? One away in this direction and one away in this direction. It was the same change, right? These are both a change of 1. Now notice, this was a change of 1 from here to here. This was a change of 4 from here to here. This was a change of 9 from here to here. This was a change of 16 from here to here. So that's kind of our basic, that follows our regular quadratic path. Change of 1, 1 squared is 1. Change of 2 from here to here. That's why this changes by 4. Change of 3, 1, 2, 3. These changed by 9 because 3 squared is 9. So again, if this is our vertex, everything mirrored. So if this one was 5, this one should be 5. If this one was 10, this one should be 10. Now we can start plotting our points. Remember, our vertex was at negative 2, 1. So right here is our vertex. Then at negative 1, we're at 2. Also at negative 3, we're at 2. At 0, we're at 5. And again, that one should also make sense because that should be our y-intercept. And then again at negative 4, we're at 5. 1, we're up at 10. -5, we're up at 10. Everything else goes a little too far off the chart. So those are our dots. We would just connect them, and there's our parabola. So again, you can always use the table to help you find your a few points. That way you can make a graph from it. Just be sure, find the vertex first and center everything around that vertex. What happens when a is not 1? So like in this example, again, we still have our ax squared plus bx plus c, but notice our a value isn't 1 anymore. This is a 2. So we'll come back to this example in just a second. I want to show you some things that would happen, again, according to our table. If we just use the regular y equals x squared, we've looked at this a little already. We can see, again, our input of x gives an output of y here. We can see things like 9, 4, 1, 0, 1, 4, 9, and up to 16. Now let's say in front of that we had a 2, so a 2x squared. All we're doing is just changing everything by a factor of 2. So after you plug in your x, it gets squared, so -3 squared is 9. 9 times 2 is 18. So notice how much bigger all of these things are. So instead of 9 to 4 to 1, it's 18 to 8 to 2. Same thing when our a value is 3. These are all 3 times as big. Now I also want you to look at the change there. So again, going from, I'm going to go upwards actually, going from 0 to 1, when our x was 0 to our x is 1, the y value changed by 1. Going from x being 0 to y is 2, so we had a change of 2, it changed by 4. How does that change over here? Instead of changing by 1, this one changed by 2, so it was twice as big. Instead of changing by 4, this one changed by 8, so again, it's twice as big. So basically all of the changes, I want you to focus on the change, not necessarily these points. Don't think about the 0.11 or the 0.24. I want you to think about the change. As x changes by 1, y changes by 2. As x changes by 2, y changes by 8. If our a value is 3, then we can see as x changes by 1, going from one box down to the next, our y value is changing by 3. If x changes by 2, our y value is changing by 12. Okay, and again, this is from the vertex. This only works for going from the vertex. Notice this change of 1 isn't 3. This is a much bigger change. This is 15. But we're just going from the vertex. If we start here, as we go over 1, we're going up 3. Over 2, we're going up 12. Over 3, we're going up 27. So all of those changes, those growths, are getting much, much bigger. How about when your a value is smaller than 1, so like a fraction? Well, again, all we're doing is taking all of these values, what the y's were before, and just multiplying them by that factor, that 1/2. So instead of 9, it's 9/2, or 4.5, or 4.5. Instead of 4, it's 2. 2 is half of 4. Instead of 1, it's a half. 0 is still 0. 1 is a half. 2 or 4 would be a 2, and so on. How about one like 2/3? Same thing. We're just doing 2/3 of each of these. So again, you can kind of see, as we look at our changes, as our x goes up by 1, or should I say goes over by 1, our y value is getting bigger by a half. As our x goes over 2, our y is getting bigger by 2. As our x goes over 4, I'll jump way down here, our y is getting bigger by 8. So as long as you're starting from the vertex and you know your a value, you should be able to figure out how much it's getting bigger by. Okay? You don't have to fill this table out. I'm just trying to show you what's going on here. So, again, just kind of a visual representation. When a is 1 and we come from the vertex, so if we start here, Obviously, when x changes by 0, y is going to change by 0. It's not going to move. When x goes over 1, y goes up 1. When x goes over from the vertex 2, y goes up 4. When x goes over 3, y goes up 9, and so on. So again, these are just the changes by. These tables you might want to write out. This table for reference comes from a equals 1. This is our regular equation when the a value is 1, so there's nothing in front of that x squared term. Okay, these are the changes that you'll notice, again, from the vertex. You have to start at the vertex. When our a value is 2, so notice this red parabola is still that just a regular a equals 1, so x squared. But if we start again from the vertex, this time, when our a value is 2, if x changes by 1, so come 1 over, our y actually jumps up 2 instead of 1. If x jumps over 2, our y is actually jumping up by 8 instead of by 4. If x changes by 3, our y changes way up here off screen at 18, which is double what it was. Again, this would normally just be a 9 right here, but it's twice as big. So you can see that when a is 2, this gets a little bit more narrow because it's growing so much faster. Now again, I want you to write this down and use this as a reference chart, as long as you're going from the vertex. So even if the vertex was right here, if my a value is 2, I would know I can go over 1 up 2. I can go over 2 and then up 8. So 1, 2, 3, 4, 5, 6, 7, 8. There and there. So even though my vertex was way over here, it wasn't here anymore, I go 1, 2, 2, 8, 3, 18, and so on, and that's how I can graph out my parabola. When a equals 3, here would be our reference chart. Same thing. Again, here's our vertex, over 1, up 3 this time instead of up 1. Over 2, up 12 this time instead of 4. Over 3, up 27 this time instead of up 9. So you can see how much quicker these ones are going to grow. When your a value is bigger, it grows a lot faster and it makes it more narrow. When our a value gets smaller, so we're using a half. These were supposed to be different colors. I think the top one is supposed to be pink and the bottom one's supposed to be red. The top one here is a equals 1. This bottom one, this is your 1/2. So again, if we start here at the vertex, instead of going over 1 up 1, we're only going half of the way there. Instead of going over 2 up 4, we're only going half of the way there, just to 2. Instead of going over 3 up 9, we're only going half of the way there to 4.5. Or you can call it 9/2 or 4.5, 4.5, what do you want to call it? Instead of going over 4 and up 16, we only go half of that, up to 8. So you can see with our a value equaling a half, we're growing a lot slower. So it kind of widens out the parabola. When your a value equals a third, again, so here we have a better visual, different colors. We can see 0, 0, 1 only goes up a third. 2 only goes up 4/3 or 1 1/3. 3, instead of going all the way up 9, it only goes 3 because it's a third of that 9. Instead of 4 going up 16 way up here, it only goes a third of that, so 16/3 or 5 1/3. So everything is growing a third of the rate. It's only going a third of the way as high. So that's why, again, this blue one, you can see it's a lot wider than the red one was. So make sure, again, you have these written down, because if you have a vertex way out here, you should still be able to plot these points. Over 1, up a third. Over 2, up 1 1/3. Over 3, up 3. That one will probably be the most important when you can find over 3, up 3. So the ones right on the whole number parts. Same thing if we have a equals 2/3. Instead of going over 1, up 1, it only goes up 2/3 of the way. Now 2/3 is pretty close to 1, so you can see how close these are, but over time you can see that they do get spread out, because it is only about 0.6 or 0.6 repeating, so it's not quite 1. When you go over 2, you're up 2 2/3, not quite to 3. When you go over 3, you come up to 6. So again, this one is kind of nice because this is a whole number spot. So you know that for sure when I come over 3, I can go exactly up to 6. And 4 would go up 10 2/3. I'm going to do a couple more when our A value is 1/4. So again, here at 0, over 1 up 1/4, over 2 up 1. So again, this is a nice spot because it gives us whole numbers. Over 3 up 2 1/4. Again, how we did that was 3 squared is 9. 9 times this 1/4 is 9 over 4, or 2 1/4. And over 4 up 4. So this one is kind of nice because it has these two different whole number parts. Over 2 up 1 and over 4 up 4. And one more, we're going to look at A equals 3/4. When A equals 3/4, again, you can go right here at the vertex, over 1 up 3/4, over 2 up 3. So again, this over 2 up 3 is kind of a nice spot because that's whole numbers. Over 3 up 6 3/4. So it's not quite touching. And over 4 up 12. So that one is touching right on that whole number part. So two different whole number pieces again. So again, make sure you have some of these written down so you can look back and use this as a reference guide to say when my A value is different from 1, I know from my vertex how far to go over and up, and then over and up, and then over and up from the vertex each time. So we're going to come back to that one that we were talking about before, kind of at that very first sheet, that y equals 2x squared minus 4x minus 5. So how would we graph that one? Well, let's check it out. We're going to use our negative b over 2a to find the x value for our vertex. So negative b, our b value is negative 4, so we would use 4, a positive 4, because it's negative b. 2a, 2 times 2 is 4, so we have 4 over 4, which of course is 1. So our x value is 1. So when we make our table, we want to make sure it is centered around 1. Let's plug 1 back in here. 1 squared is 1, times 2 is 2. 4 times 1 is 4. So 2 minus 4 is negative 2. Minus 7 is a negative 7. Or sorry, minus 5 is a negative 7. So this is going to be our vertex. We are at 1, negative 7. Sorry, negative, shoot. I got to get this here. Positive 1, negative 7. My bad. So all we need to do now is just plug in values or points that are around our vertex. If we wanted to, we could go through and plug them each into here and solve it and figure out what we got. Or, remember, we have our reference guide for 2. When a equals 2, what is happening from our vertex? Instead of going over 1 up 1, it's over 1 up 2. So here and here. Instead of going over 2 up 4, oops, 4 will be here, it's actually over 2 up 8. So 4, 5, 6, 7, 8 here and here. Instead of over 3 up 9, it's over 3 up 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. A little bit higher on 11 is 18. So again, these would be the points. I found these using my reference of a equals 2. So I know that that's how everything works. As a double check, notice that our y-intercept should be -5. As we cross the line here we are at -5. So everything should fit in line there. So this is what our parabola should look like. Going up from there. So that'll do it for our second video. We've discussed using tables. We've discussed using a is not equal to 1 in standard form. And we've done our a equals references. So again, things like a equals 2, a equals 3, a equals a half, a equals a fourth. I would write some of those down, and you can use those while you are working.